Good morning. So let's go ahead and finish up chapter 4. That will be everything that is through the first exam. Again, I haven't got it put up there just yet, but your exam will be on Moodle. Let me share my screen. So I'm still making some adjustments on the test. But right around here where like the Zoom meetings laboratory resources are, there'll be a tab and it just says tests, and you'll click on it and it'll be a multiple choice test. I'll show you one of my other courses and how that looks. So if I go to my 151 class, you'll see here I've got a section for tests. So there will be the test available for you. I've got to get ours up. You'll click on it and then get started. You'll have an hour and 15 minutes to take the whole exam, and it will start at like 5 a.m. on Sunday. So you can get up real early and do it on Sunday, all the way through Monday at midnight, because I know some people work on the weekends. So we've got one weekend day to do it or one weekday to do it. As far as on Monday, we will just like continue to lecture forward. We won't go over the exam until Wednesday, because there will probably have been some people who haven't taken it yet on Monday. So there you go. All right, let's pull up our lecture slides. All right, so we finished off talking about, we've got our periodic chart. Hopefully you know where the metals and the non-metals are. You have a general idea of where the metalloids are. You've got your columns, so column 1, you've got, well, we've got our main groups, which is column 1 through 8, which are those guys that stick up a little bit higher. Let me pull up periodic chart here. Okay, we've got our main groups here. We've got our transitions here. We've got our alkali metals, our alkaline earth metals, our halogens, and our noble gases. I think that's about where we left off, yeah. All right, so we had talked about how you can't change the number of protons, right, for a given element. So let's find carbon on the periodic chart. Carbon has an atomic number of 6. So that means it has to have 6 protons. Can't change the number of protons. If instead of 6 protons, we had 7 protons, we would no longer be carbon, we would be nitrogen. So you cannot change protons, but there are ways for atoms to change both the number of, or to have varying amounts of electrons and varying amounts of neutrons. So as far as electrons are concerned, we talked about how metals like to lose electrons, right? Things on the left side of the periodic chart, these guys over here, they will lose electrons to form what's known as a cation. So any particle that has gained or lost electrons in the way that there are more or less electrons than there are protons is called an ion. An ion just means that it's a charged particle. So when you hear like ionization or, oh, I have this like ion brush for my dog and it sounds super fancy, right? All it is a charged particle. So we can either have positive ions, which are called cations, or negative ions, which are called anions. And next to that, cations lose electrons. Anions gain electrons. And that always seems to throw people off because the idea is like, well, if I'm losing something, I should be negative, right? And if I'm gaining something, I should be positive. But what are you losing and gaining? If you're losing an electron, remember the electron is sort of that negative person in your life, you're going to become more positive. So electrons have a negative charge. Okay, negative charge. So cation positive, anion negative. If we happen to be dealing with a charged particle, how will that look? Well, we write the symbol and then we put the charge in the upper right-hand corner. Okay, so here I've got magnesium with a 2+ charge. Oxygen in the upper right-hand corner, I've got a 2- charge. So just know when you see something like this, sulfur versus sulfur with a 2- charge, those are slightly different. All right, they still are sulfur, they have the same number of protons, but this sulfur down here is actually holding on to 2 additional electrons. Usually the way that it's written is you do the magnitude and then the symbol after it. So it would be like 2+. If you're writing +2, that's okay. But traditionally you'll see the magnitude first and then the charge afterwards. So let's look at lithium. So lithium is in column 1. Lithium likes to give up an electron. So over here, we've got lithium. And in this case, this lithium has, how many protons does lithium always have? Look at your periodic chart. What is its atomic number? It's sitting at number 3. So lithium always has 3 protons, 3 Ps. In this lithium over here, I'm charge neutral because I don't have a charge in the upper right-hand corner. So my number of protons should equal my number of electrons. So there's also 3 electrons here. Okay, 3 and 3 gives me a 0 charge. Over here, when I've become lithium plus, I still have 3 protons. That doesn't ever change if it's lithium, but my electron number has changed. If I'm a +1, that means I've gotten rid of an electron. I now have 2 electrons. Here's the other electron, the 3rd electron. Okay, so that's how to read this. You had lithium and it sort of discarded an electron. So your ion charge will always be the number of protons minus the number of electrons. That's a real simple way of calculating it. So for lithium with the plus charge, we have 3 protons, it has 2 electrons. Your overall charge is +1. Okay, in the other direction, if we go over to fluorine, this fluorine written here, if we don't exclude the electron, we're just looking at this right here. This fluorine has how many protons? Look on your periodic chart. What does fluorine always have? You should come up with 9, okay, because its atomic number is 9. So protons here is equal to 9, and electrons here are also equal to 9 because it's charge neutral. Now, when we're reading this, what we're saying is that fluorine is going to eat up an electron to become F-. If we go to this thing over here, this anion, the number of protons is still 9. The number of electrons, though, has increased to 10. Originally, it would have 9 electrons. If it's a negative charge, we have added an electron to it. Okay, so again, ion charge, number of protons minus number of electrons. In this case, we've got more electrons, so our negative value is greater by a factor of 1. So you will need to be able to calculate those. We'll run through a couple in just a minute. Protons are really easy to calculate. You just look at your periodic chart. Electrons, if it's a charged particle, you got to do a little extra work. And remember, positive charges, less electrons. Negative charges, more electrons. Okay, I'm going to clear this out. So, forming ions of main group elements. So remember we distributed or we defined our periodic chart into main group elements and then transitional metals. So my main group elements was column 1, column 2, and then the 6 columns on the right. We like those main group elements because they tend to have a very specific charge. They form a predictable charge every time because they have a consistent number of valence electrons. Column 1 has 1 valence electron, column 2 has 2 valence electrons, column 3, which is not the transition metal, skip over to boron, that has 3 valence, 4, 5, 6, 7, all the way to 8, okay? 8 valence electrons. A valence electron is just the electron in the outermost shell. We're not going to spend a whole lot of time. We'll come back to electrons later. But 8 valence electrons is particularly stable. So the noble gases at the very end, they have 8 valence electrons. So they're happy. That's why they don't tend to bond. So the key to predicting the charge acquired by an element is its position in the periodic chart relative to the noble gases. All right, so where something is located in relationship to the noble gas is going to give you an idea of what charge you get. So let's look at the charges. Here they are. So above column 1, I want you to put +1. Okay. On your periodic chart, above column 1, put +1. Hydrogen, when it's acting as a metal, forms an acid. It does form a +1 too. Like if we had, for instance, HCl, this is a +1 on this thing, hidden in there. But this would be an acid, so we don't really consider it a metal and a non-metal. We'll get into that later. So know that hydrogen also will sometimes like to form a plus charge. Okay. So we've got +1 here. Now look at where we are on the periodic chart. If I'm at lithium and I am a +1 charge, what happens is I lose an electron. So instead of being like lithium as my electrons, what do I behave like? Go to the element before lithium. You have to go back to helium. So lithium is now behaving like helium. What about sodium? Sodium also forms a +1 charge, which means it loses an electron. If we're at sodium and we go back 1, what do we like? Now we're like neon. So it's behaving like a noble gas when it loses 1 electron, all right? Over column 2 here, we're gonna put a +2. Because everything in column 2 likes to give up 2 electrons. Why? Because if I'm at, let's say I'm at beryllium, if I give up 2 electrons, I'm gonna hop back like lithium and then back like helium. Right? If I'm calcium, I'm gonna hop back like potassium, and then I'm gonna hop back like argon. So everything's sort of trying to become like a noble gas. That's why those have predictable charges. So put a +1, put a +2. Above column 3 over here, not including boron, okay? Because boron is a non-metal. We're going to put a +3. So those guys like to give up 3 electrons. Go over to column 5. So skip carbon and silicon. Those guys can kind of do either or, give and take electrons. But if I go to column 5, I want you to put -3 or 3-. This thing likes to take on 3 electrons. If it takes on 3 electrons, 1, 2, 3, it's just like a noble gas, okay? Oxygen, that excuse me, that whole column is a -2 charge. Fluorine's column, fluorine, chlorine, bromine, that's a -1 charge. Okay, these numbers are important. We're going to use them like over and over and over and over again. Above your noble gas, you can put like a 0 with a strike through it. Those guys don't form a predictable charge. What happens with transition metals? Transition metals are tricky in that they can have varying charges. Okay, so you don't need to have those memorized, but there are a couple that have predictable charges within the transition metals. So go to aluminum on your periodic chart. That is a 3+. Go in a diagonal down order. The next one here is zinc. Zinc has a 2+. The next one here is silver, Ag, that has a 1+. Okay, so 3, 2, 1. So you do need to know those, 3, 2, 1. You do want to know those charges, that they're predictable. So we've got our +1s, our +2s, our +3s, our -3s, our -2s, our -1s, and then we've got 3, 2, 1. So, okay, so we're not going to get into isotopes yet. Let's do a couple of these. I'm going to clear this out. So make sure you have your periodic chart with the charges on it. Let's go down to so embedded with the slides here are always like additional worksheets and stuff that you can use if you want some extra practice. So in here, okay. So these are for sorry. These are for predictable charges, elements. So I want you to do, let's do aluminum, sulfur, nitrogen, and bromine. Okay. I want you to tell me how many electrons it gains or loses, what its ion is, and then whether it's a cation or an anion. So just look at those charges that you have and go from there. It shouldn't be too complicated as long as you have the right charge written on your periodic chart. Just another 30 seconds. Okay, so for this first one, aluminum, when I look at aluminum and where it is on the chart, I know that this thing is going to lose 3 electrons. And it's going to become Al, 3 plus, and remember that a plus is a cation. Sulfur, where sulfur is situated on the periodic chart, it likes to gain or eat 2 electrons. This will give us an S with a 2 minus charge, and this would be an anion. Nitrogen is over in column 1, 2, 3, 4, 5. So this guy likes to gain 3 electrons. And with a 3 minus charge, this is an anion. Bromine, all the way down there at 35. He likes to gain 1 electron to form Br minus. This is also an anion. Okay. If I was to give you something like iron, 26, you wouldn't be able to tell me the charge on it because it's not in our main group elements. It can have a varying amount of charges. Now, I think just remember aluminum, because I think Suzanne, you stepped away. Aluminum is a 3 plus charge. Zinc, go down and to the left at an angle. So aluminum is a 3 plus, zinc is a 2 plus, silver is a 1 plus. So just in that zigzag line, it goes 3, 2, 1. Don't want to forget that. So all the other ones have unpredictable charges. Okay. Let's go back over to our slides. So now we're good with elements, we're good with ions, and that we know the charge. So we're going to move into one more thing, which is known as an isotope. So an isotope is the same element, so it has the same number of protons, but the number of neutrons will vary. All right, we'll have more or less neutrons. Now, remember the characteristics of a neutron. A neutron doesn't have a charge, so it doesn't change the charge, but it does weigh as much as a proton, so it will change the weight. So shifting neutrons changes weight, not charge. Electrons or ions is a change of charge, but not weight. So there are a few exceptions to this rule, such as boron, but we're not going to talk about that. Okay, so all atoms of a given element have the same number of protons. They do not necessarily have the same number of neutrons. When we have an atom with the same number of protons, so it's the same element, but different number of neutrons, we call it an isotope. All elements have their own unique percent of natural abundance of each isotope. So for instance, carbon has a lot of carbon-12, a little bit of carbon-13, and a little bit of radioactive carbon-14. Most of it is carbon-12 though. These natural abundances are consistent throughout, I say they're relatively consistent throughout the universe. So, and if you've heard of isotopes, there's 2 different types of isotopes. So there are stable isotopes and unstable or radioactive isotopes. Radioactive isotopes are the ones that you think about being in a nuclear bomb or a nuclear plant. They decay because they're so big and their nucleus has so many neutrons in it, it's so clunky that it'll break down. Stable isotopes are isotopes that they have a different number of neutrons, but they don't decay or they don't break down. Okay, so let's look at neon. So neon is got, if we look at our periodic chart, neon has a number, atomic number of 10. So it has 10 protons. But if you look at the mass isn't exactly 20, right? It's 20.179. And it's like, well, why would the mass be a decimal? Because how can you have decimal protons or neutrons? You can't. The reason that that has a decimal of 20.1797 is because it's averaging out all of the different isotopes that exist in nature. So in a neon light here, we've got most of it is neon 20. In this case, it says 90.48% is the neon 20. A small percentage, smaller percentage is the neon 22, and then a very teeny tiny amount, 0.27, is the neon 21. And what do they mean when they're writing neon 20, neon 22, neon 21? They're changing the atomic mass for each of these. So this is neon with a mass of 20, this is a neon with mass of 22, this is neon with mass of 21. If we are neon, how many protons do we always have to have? 10, right? 10 protons. Can't change that. So if I'm dealing with neon 20, 10 of those are protons. The number of neutrons in this one is also 10. What about neon 22? Well, if we have a total mass of 22, 10 of them are protons, the other 12 will be the neutrons. Whatever's left over is the neutrons, okay? Neon 21, protons is 10, what's left over? 11, that's the number of neutrons. Okay, so that's where these numbers are coming from, where it says 10 protons, 10 neutrons, 10 protons, 11 neutrons. You will not have to have every isotope that exists memorized, okay? Some of them have quite a few isotopes, but I do want you to be able to read this. So if you were to see this, neon 21, and I would say, how many neutrons does that have? You would be able to calculate that. And it's really basic, right? You just subtract the number of protons. There's a couple different ways that you can see it written. Isotopic symbol notation, okay? So sometimes it's written like this. So you've got them down here. There's neon 20, neon 21, neon 22. You have the chemical symbol, and then in the upper or the forward left corner is the atomic mass. That's the protons and the neutrons. Then you have the atomic number, which is the number of protons. This way, for me, it's sort of redundant, right? Because if you know what element it is, you already know this number, right? Those are bound to each other. That's why it's 10 at each one, because they all have 10 protons. This is the number in the upper left-hand corner that's going to shift. Now this number is different than the charge, right? When we were talking about S2 minus, where did we put the charge? We put the charge on the back end, okay? So don't get that confused with this. This is talking about a change in mass or number of neutrons. This is talking about a change in charge or number of electrons. So just again, the number A is the sum of the number of protons and the number of neutrons. So when we want to figure out the mass number, it's the protons and the neutrons. Or if we want to find the number of neutrons, we know the mass and we know the protons. We can figure that out. Here's some other ways that it's written, neon-20, or they write the whole thing neon-20. So just be okay with seeing isotopes written in a couple different ways. So if I write, let's say we're dealing with radioactive carbon-14. I want you to tell me the number of protons, the number of neutrons, and the number of electrons in this thing. Oh. Okay, sorry, get that mute off. If we're dealing with carbon, the number of protons is always consistent. It should always be 6. 6. The number of electrons in this thing there's no charge in the upper right-hand corner. So my protons and my electrons will equal each other. So it should be 6. I don't know why that's doing that. Your screen sharing is paused. Sorry, I stopped sharing for a second. My computer's not happy again. So we had carbon 14. Oh. Sorry guys, give me just a second. Susan's over here. Okay, carbon dash 14. So protons should always be 6. We said electrons will also be 6 because we're not dealing with the charge. The only thing that's changing here is the neutrons. So if I have a total of 14 and 6 of them are being occupied by the proton, well, 14 minus 6 will give us 8. So we'll have 8 neutrons. So you want to be able to do that. Okay. So the last thing I want to talk about is calculating the atomic mass or the average mass of each element. So like when we're looking at that periodic chart, let's look at chlorine. Chlorine is number 17. The atomic mass on that thing is 35.452. So that's because we have some chlorine 35, we've got some chlorine 37. And the natural abundances or the average of the natural abundances are overall giving us that decimal. So how do we calculate that? It's kind of like when you calculate your grade in a class and 60% of the grade is tests and 10% is homework. It doesn't matter if you have 100% on homework. If you're not doing well on the tests, you're not going to do well in the class because it has a bigger weight to it. So the way that we're going to do that is we take whatever the percentage is, you have to move it into its decimal form. So you divide it by 100 or you move the decimal over. You take its percent in decimal, you multiply it by its mass. In this case, it says chlorine 35, but it says its actual mass is 34.97. If it gives you the actual mass, use that. If it doesn't give you this, just use 35. You can just do it with the base number. So you take the decimal version of this, which is here, and you multiply it by the mass, and then you add it to the same things in other isotopes. So here I've got the 24.23. I'm going to move that decimal over to 0.2423, multiply it by its relative mass. And then you multiply these, and then when you add them together, you get an overall weight. In this case, it's 35.45, which is consistent with what's on the periodic chart, right? This number needs to lie somewhere between this and this, right? If you're averaging these two things together, it should fall between those two. If you have a B in homework and you have a C on the tests, your overall grade is not going to average to an A. It has to be somewhere within that range. So one way to check is make sure this number is falling in between those two numbers. If it's not, you've done something incorrectly. So here's the like generic equation for it. So you take the fraction of the isotope times the mass of the isotope, and you add it to the fraction of isotope 2 times that's mass plus the fraction of isotope 3 times that mass, so on and so on. So if you have 16 natural isotopes, that problem is going to take a really long time. But I would probably only give you something that has 2 or 3 natural isotopes, okay? So go ahead and do this one. We've got gallium, and it says gallium has 2 naturally occurring isotopes. There's gallium-69, but it actually has a mass of 68.9256, so we use that. And that's natural abundance is the majority at 60.11%. Then we have gallium-71, which has an actual mass of 70.9247, and that's at 39.89. So I want you to calculate the atomic mass of gallium. Flash back to the equation. Yeah. Right here. So it's the fraction isotope times its mass plus fractional isotope times its mass, isotope 1, isotope 2, isotope 3. For this one, you only have 2 isotopes, so you just need to use the first 2 slots. Okay, I'm going to swing back to that problem. Just another 30 seconds. Okay. So first thing when you're doing one of these problems is get your percentage into a decimal form. So in that case, take them and divide them by 100. Because what is percent? Percent, cent, is like a cent in a dollar, right? Per 100, or a century per 100. So we want to get rid of the percent. We divide it by 100, so you should get a decimal for both of those, 0.6011, 0.3989. Easy way to do it is just move the decimal to the left 2 spots. From there, we'll set it up in our equation. So we'll take the weighted percent and multiply it by its mass. And then we add it to the weighted percent multiplied by the mass. All right. We end up getting these two values, 69.72. I'm not going to be super anal about sig figs with this, but usually you honor 2 sig figs or 2 decimal places. Why? Because this had 4 sig figs. So this thing will have 4 sig figs or 2 decimal places. Yes, no, maybe so. Yeah, thumbs up. Okay. Let's just do one more of them just to really get it in there. Also because that's the last thing that we have to do for the first test. So we'll do one more and then you guys will be free to go. I've got a bunch of practice of these in your Moodle worksheets. So if you want to do even more practice, there's more in here. Let's do, oh, I'm not going to be mean. I won't do that. Let's just do the first one, okay? For rubidium. So let me try and zoom in here. There we go. Rubidium is a silver white metal that has 2 common isotopes, rubidium 85 and rubidium 87. If the abundance of rubidium 85 is 72.2% and the abundance of rubidium 87 is 27.8, what is the average atomic mass? This is an example where it doesn't give you the very specific decimal. You see how it just says rubidium 85? So just use the number 85 as your mass. I'll give you all 2 minutes or so, 2-3 minutes. Okay. So first thing I need to do is get these guys out of percent. So divide by 100, divide by 100, or move the decimal over 1, 2. 1, 2. Okay. So the first isotope has a decimal fraction of 0.722, and we're multiplying that by 85. We're going to add that to the second thing, which is got a decimal percentage of 0.278 times 87. So most of this thing is 85, right? A little bit is 87. So my guess is that my number is going to sit closer to 85 than it would to 87, but it has to be somewhere in between those. So we've got 85 times the 0.722. All right, so this top number is 61.37. The bottom one, 0.278 times 87. This guy will equal, we're going to add these two, right? We're going to add these two, 24.186. All right, so my total is 85.3 sig figs there. I'm going to go with 85.6. And the units on this are AMU. Okay. Not too bad. The number is off because the chart does that because they didn't give exact masses. Yeah, let's see, where's rubidium? Rubidium there, they've got 85.46. Yeah. It may not always be exactly what is on your chart. Good question though, Harley. So as far as the test is concerned, it will be all multiple choice. If people, I think there's one or two people that have taken a class with me before, I usually would give short answer at the end so that I could give you guys partial credit if you sort of knew how to do it. That's not going to be the case for this exam, okay? It's going to be probably about 40 questions, all multiple choice. So don't let the multiple choice flip you up. Make sure you're reading the problems over, read every answer. I want you all doing well. You are allowed to use your notes. You definitely want to have a periodic chart right off the bat, have a periodic chart handy. And then I will show you in here in Moodle, there is a handy formula sheet. It's also in your, I believe it's in your lab manual as well. Where is it? Oh, here. So this may be something that you want to have handy or printed off. This is what traditionally what we would give you on an exam. If it was in person, you would get a periodic chart and you would get this. So this has like a bunch of just formulas that we use pretty regularly. For the first exam, like none of this is going to be used. Okay, you're really just sort of going to be in this area here. Well, there's this here too, right? We've got our energy. We won't be using moles at all. So that would be a useful thing for you to have just readily available. So you are all good to go. Yes, email me if you have any questions. Or stay around if you want to ask any questions. Feel free to start taking the test on Sunday if you want. Otherwise, you can wait until Monday. Just make sure you get it done by midnight on Monday. All right, you guys have a good day. I'll see you next time. Have a good weekend if I don't talk with any of you.